Oh, there we go. Hey, everyone. Cool. So today I'm going to be talking about this paper, which was released by a few people from Netflix, around what's the deal with cosine similarity, and does it actually represent similarity, and is it a good measure to be using when we want to compare two objects and their using their vector representations. I picked this paper because, well, A, I saw it on Twitter and I thought it looked interesting, but B, I thought that given all that's going on with LLMs and specifically with RAG, like cosine similarity is being used a lot in terms of for retrieval reasons. But obviously there's, it goes back much further than that into the world of like recommender systems and things like that. And I've personally always gravitated towards cosine similarity. It's just like, oh, I want to get things working. I want to get things going. Let me just use cosine similarity if I want to do any kind of comparison of like two vector representations. So it intrigued me. It piqued my interest. I was like, okay, let me see what they've done. It's quite a simple. It's a short paper, so this paper club might be short, but I have a few questions prepared afterwards for maybe a bit of discussion. As Peter said, please feel free to interrupt me at any point. I want this to be like as interactive as possible. Let me hide the sidebar. Cool. So what's this paper really about? So what they want to understand is how effective is cosine similarity at representing actual similarity in the real world, and how is cosine similarity impacted by how we train or how we come to obtain the like vector representations for whatever we're representing. So as they mentioned, cosine similarity is obviously very popular measure, and it's shown to be quite effective in certain cases, although in other cases it's shown to be ineffective, or there are other methods that beat cosine similarity depending on the use case. And what they want to understand is like how they want to sort of get a reasoning for why does it work better in certain cases and worse in other cases. Can we find some kind of explanation or begin to explain this phenomenon? And how they do this is they've created they run a small experiment which is quite simple but effective in showcasing that there are things in the way you train your model can impact the effectiveness of like cosine similarity further down. So based on this, what they advise is do not blindly use cosine similarity. I think the conclusion is basically, which is kind of common sense, is probably depends on your use case. You might want to test different ways of measuring similarity. Don't just gravitate towards it with no testing. So I think hopefully people here are familiar with cosine similarity and its value, but obviously when we learn like embeddings of things, and in this case they use the example of like recommender systems, presumably because it's Netflix and that's like a core of their business. So often when you train these kind of recommender systems, you could also it creates like embeddings of the items, in this case would be like TV shows or films, and then the users of the product. And you can then use these embeddings to try to understand like the similarity between users and similarity between items, and also affinity between like users and items. I guess the context of the paper, as I mentioned, is the fact that sometimes the cosine similarity is effective, but other times it's shown that it hasn't been as effective. They give a few examples of like alternative methods that have been shown to outperform cosine similarity in different use cases. One which I definitely like recommend to reading is the Colbert paper, which I think is quite a cool paper and method generally for doing for doing like similarity search, but I won't go into detail about it today. So what the experimental setup, or what they want to do, is they want to show that that cosine similarity can be affected by the training setup, and in this case, they explore the impact of like regularization on the output embeddings, and therefore the effectiveness of cosine similarity in answering the question, how similar is this item to this item? And they show that, they show that by looking at linear models. In this case, they look at matrix factorization models. The reason they do this is because it's a simple, it has like a closed form solution, and so they can sort of derive how the sort of the solution, and then how that might impact the embeddings, and then therefore the cosine similarity of those embeddings. Cool. So matrix factorization is like a popular way of like of going from, let's say you have a matrix of like users and interactions and items, sorry. So you have a matrix basically describing how users have interacted with items. In this case, either they've viewed a TV show, or maybe they've rated it, or maybe they've, in the case of e-commerce, they've like bought certain items. And what we want to do is we want to take this matrix of interactions and try to derive like embeddings of like users and items. And that's valuable not only to do the similarity search, but also you can use these embeddings for downstream models as well. And matrix factorization is like a simple way to, a simple approach to solving this problem, where you basically take the matrix and you try to approximate it using like a low rank matrix. So let's say you have n users and p items. You would have these two matrices A and B, which have dimensions p and k, where k is significantly smaller, right? So you go from, let's say you have 10,000 items, k could be like 50, so you have like a smaller dimensional embeddings for the users and for the items. And yeah, afterwards you can use them to do similarity. So they compare these like two different ways that you could train a matrix factorization model. So they look at two different regularization schemes. The first is this one here, which they mention is kind of equivalent to doing like dropout or denoising. So effectively, you're like you're forcing the model to like disregard certain features, I guess, when you're training it. And then the second one is where they regularize like the matrices independently, and that's more like weight decay. So you make sure that the weights of, or the weights of those matrices aren't like too big, which could suggest like overfitting. And the reason they pick these two is because they have like, they impact in different ways. Well, they obviously they have different closed form solutions, and then therefore they impact like how they might the resulting like cosine similarity. So this is where it starts getting into the meat of like the results in the paper. So here they're looking at the fact that you have, let's say, the two solutions, A hat and B hat, and they're like you can apply like different rotations, and they're also solutions. And while like the cosine similarity of like the items will remain the same under those rotations. In the first example, so the dropout denoising example, they find that the cosine similarity, the solution is invariant to like rescaling of the columns of A and B. However, that impacts the cosine similarity. So cosine similarity is not invariant to the scalings of the columns A and B. So effectively what we're saying is you can scale the columns of A and B and you achieve it's effectively the same solution. However, that will change the resulting cosine similarity of those embeddings. And they demonstrate this using, well, it's actually like a fairly like straightforward derivation where you have like a diagonal matrix D, and you show that the AD and BD inverse like is also a solution to the matrix factorization problem. However, when you look at the it affects the normalization, and the cosine similarity is effectively the same as the normalized dot product. So because they have like because it affects the normalization, therefore it affects the cosine similarity. And so this is what they show here, that looking at item, item, user, user, and user item, they all depend on this arbitrarily chosen matrix D, which is used to scale A and B. So therefore, even though the solution is invariant to the scaling, the cosine similarity is impacted by it.
Excuse me, one quick question. Yeah. I was slightly struggling with the problem setup, right? Normally, you would think that the problem is to some extent symmetric, that you can exchange the items for the users in. You would have a similar problem if you were to do this sort of clustering. I think from the problem setup, that was not quite the case, right? So they have the way they framed it as A and B having to have equal dimensionality, that they sort of have already like some sort of choice in there in their setup, no? I might have gotten this completely wrong as well, but
so A and B do have the same dimensionality, but then XA is the user embeddings, and then B is the product embeddings. So you can still have different combinations of N and P, and still and this still holds, right? Unless I misunderstood your question.
But we could equally well say that no, never mind. I think wait, P was the dimension of the
items or the features, yeah.
Yeah. And so we could in principle formulate it as the dimension of the users as well, right? So then
sure, yeah.
And would that be different, or should a symmetric version of those two options be a more meaningful problem to solve?
Would that not be equivalent?
That I'm not sure.
Yeah. Matt.
Oh, I think, Arvid, I believe I had a different understanding. I think it was that the whole point of using cosine similarity was because they had assumed that the scaling of the vector, how big it is, does not matter. It won't change the similarity. But this paper is proving otherwise. I thought that was the intuition, but yeah, correct me if I'm wrong.
I think you're not wrong at all. It's more the problem formulation as x proportional x a b t seems to favor the dimensionality of the the items where of course the problem in principle could be flipped around, but I could put my users on my columns of the matrix and have the items as the thing, because it's a sort of overlap problem, right? And I don't know for sure how much of that formulation actually favors one of the others, which makes this an inherently non-rotation invariant problem.
So you can generalize this to you have like you have data points in this case items or users, and the features of those things are represented. In this case, they're represented by, if you look at the items, by like the users which have bought the item. But in the case of users, it's like what items they have bought as their features. Yeah.
And I wonder if one purposefully makes that distinction go away by symmetrizing that this sort of accidental symmetry might be already breaking. I don't know. It seems slightly, I don't know, contrived is the right word here, but yeah.
Are we surprised that they're saying that the alpha are the user embeddings? Because to me, the user embeddings are not alpha, XA.
XA, yeah.
Because XA would take each user features and then embed them in a lower dimensional space.
Yeah. It's sort of the sum. It's sort of the sum of the, like, it's kind of like taking the item embeddings and summing them over like the items that the user has interacted with, and that becomes sort of the user embedding.
I was wondering to see this, if I change the number of items, I think the first objective, the regularization is effectively changes, right? Because but if I change the number of users, that wouldn't happen. And so a symmetric problem is made asymmetric here.
Because A, B only depend on the number of items.
Yeah.
Interesting.
The same way, actually, number two as well. You sort of would naturally have to ask why, in the real problem, apart from this mathematic formulation, would you ever choose those XA and B to be differently scaled? In reality, you probably would, right? Because as far as I can see, they have intrinsically different dimensions. So scaling them
XA and B.
Yeah. But not sure again.
I'm not sure I see why the dimensionality is important.
Exactly, it shouldn't be, right?
Yeah.
I guess when you're Netflix, you shouldn't care so much whether if an additional user joins or if they offer a new movie. But
yeah,
it seems in this particular case, both of them seem to matter more than they probably have. So I would suspect if we were to formulate this in a natural way where the dimensions sort of can't matter intrinsically, like I don't know, have the scaling at the regularization per dimension or something like that, then a lot of this might go away.
I see. Sure. Yeah.
Like this freedom is arbitrary, right? So the fact that this is here is because we have a product A and B, and it's under specified essentially.
Yeah. Yeah.
Sorry, that was just my musings really.
Yeah. No, no, thank you. Cool. Where are we? So going back, with the first objective, they show that you can, if you have an arbitrary matrix, diagonal matrix D that scales the solution to the matrix factorization A and B, then the cosine-similarity depends on that, and they have like an experiment where they demonstrate this, and it's actually fairly easy to code up given the simplicity of matrix factorization. they give some details on the sort of the derivation of the like closed form solution, and they give a kind of it's kind of like a funny example, I guess, to demonstrate their point, but how useful it is, I'm not sure. So they show like a special case where if they choose this D, this matrix, to be this diagonal matrix here, which is influenced by the singular values and the regularization parameter, and when you have the case where you choose K to equal P, in this case, like the number of items or the size, the dimension of the features, whatever you choose to call it, you can basically show that you can create a scenario by which the cosine similarity equals the identity matrix. So cosine similarity from anything to anything is 0 unless those things are the exact item. So yeah, again, it's a funny example. I'm not sure how useful it is, given K would never equal, you would never run this with K equals P, I guess. But yeah, and then they show that the user item cosine similarity is also just basically like the unnormalized dot product, or results in the same ranking of them. So the cosine similarity is effectively, in a ranking problem, is exactly the same as the unnormalized dot product. I guess what they're trying to show here is that is just like to illustrate a point, which is that it does impact cosine similarities in like a rather like absurd result.
I mean, in that case, in the case where K equals P, you just learn an identity matrix. You could learn an identity matrix and get an exact. So it does make sense.
Yeah. Yeah, and they show, and then I guess what they're trying to show here is that for the second objective, it doesn't really like hold as much, because there's a sort of unique solution with respect to the cosine similarity. So you can't. So this choice of regularization doesn't have the same impact on cosine similarity. So this is the like outcome of the experiment. I can talk through a little bit like the experimental setup, but basically what they did is they created they simulated a set of like users and items and user item interactions, and then applied the two different matrix vectorization models with different regularization schemes. And so what they did was they created a set of items which they clustered into 5 clusters, and then they assigned users preferences to those clusters, and then they simulated it that way. And I think the point was to try to simulate an environment where you're trying to recreate those clusters using some kind of cosine similarity. So this is the true clusters. If you look at these 3 results is basically the first regularization scheme with different scaling matrices, the diagonal matrix D. So the different choices of those, and basically showing how that can lead to like wildly different results in the cosine similarity between the items. So in this case, you can basically recreate the clusters. In this case, it's wild, I guess, what's going on. The similarity is kind of uninformative in terms of the clusters. And in this case, again, it reconstructs, but sort of less strongly to this one. And then this is the result of the second, the other regularization scheme, the weight decay one, which I found the colors a bit confusing. I was kind of had to stare at this for a while, but I think what this is showing is that there's very strong similarity. Inter-cluster similarity is very high, but there's also seemingly quite high like intra-cluster similarity with these. Yeah, so that was basically the results of their experiment. They wanted to sort of find a way to visualize this effect of how you train the matrix factorization model will have an impact on the resulting cosine similarity. I was kind of so at this point, I think we're all there, like we understand what's going on. I was a little bit like maybe disappointed at at the outcome and the conclusions of the paper, and which was the sort of remedies and alternatives are like, okay, fair enough. Like, so they mention a few things you could do where instead of doing cosine similarity on the embeddings, you can project the embeddings back into the original space, or you can think of like the normalization at different points of the training. So not just like after the embeddings have been learned, but like how do you train models where you have like normalization of the data perhaps, or like normalization within the learning process. And they give like an interesting example in for word2vec, where they did like a negative sampling proportional to like the frequency of the word, and that kind of has like a similar effect to like scaling your data before, which might have contributed to the effectiveness of word2vec at the time. I was really hoping at this point that they would go from like taking it from a sort of toy example of matrix factorization up towards what does this mean for like a lot of the state-of-the-art models that are being used today. Like I mentioned, obviously a lot of retrieval augmented generation with LLMs relies on doing similarity search, and doing a lot of them presumably use cosine similarity. So how does the training setup of these large models like impact cosine similarity? And I was hoping they'd go into that, but they kind of don't. They just kind of mention that they sort of allude to it in the conclusion, but that's about it.
Yeah, to me, parts of it seem more like a math exercise that you might see, because of what we pointed out before, like some of this stuff just upon something seems quite obvious.
Yeah,
it's still interesting to read, but
yeah. Mahad?
I know I was gonna just regurgitate what Peter said. It's a quite disappointing paper, because I was gonna assume that, oh, are you gonna extrapolate and find out how are they behaving in high dimensional order as is with LLMs, and like, yeah, that maybe could happen. So I'm thinking they've just reinvented the wheel. We already know from AI research that it's what is known as cursive dimensionality, which says that vectors tend to be nearly orthogonal to each other at high dimensions, and when you reduce the dimensions, you might lose the structure. But we already know this because we experienced the same phenomenon using autoencoders. And where's the compression happening in autoencoders? We've guessed it, the latent space. But that's why we made transformers, to avoid that latent space, to prevent dimensionality reduction. And now they're like, oh yeah, we've just found out you could do that, but we already knew it. It's a bit weird.
Yeah.
But again, still, if somebody does not understand how cursive dimensionality works in AI, which is a big thing, this is a good for a startup graduate or a first-year PhD person who just want to understand things.
Mm-hmm.
But nonetheless, I didn't. I mean, if I was a first year PhD, I would have enjoyed it. But having done that years ago, it's hilarious now.
It's kind of interesting, right? That they, because they did this is very this is the relationship, right, between the effective regularization of a layer and the update schema, and I wonder whether one can sort of train an effective objective or effective objective functional, or not train it, but maybe recover it from essentially saying, okay, we have these sort of regularizations on it, so the effective the objective must be that plus whatever comes out of the experiment. And I wonder whether that can sort of give an idea of what the model, like alternative description of what the model has learned. Say how do you put this into like a language model, right? So the language model has inherently different structure in its input space, right? It's not a feature you can't really put it as a feature matrix, or can you? Perhaps you can actually. But if you know how the input space behaves, and well, how we have regularized it, maybe there's a way to get something out of it using these insights. So that could be quite useful. Plus, it might be able to,
I can say something on that, Arvid.
Yeah.
I think it's with regularization, all it's doing is you're inducing a difference, right? The embeddings, they're meant to be same according to the paper, but when you regularize, you're causing a difference to appear. So then the problem can be reinterpreted as a Rubik's Cube, where you sort of push until two colors become alike, but then in doing so, you make two colors different. So unless you understand the input space, which is the same way of saying you understand the Rubik's Cube, then you can, of course, like be the like you've understood the distribution, how it works, but then what's the point of making an AI model if you already know what the distribution is? Do you know what I mean?
That's very fair, but perhaps more on the side of actually controlling it, right? So if I do know I want to have a certain trade-off.
Sorry, I've got a call. I'll be back in a minute. Sorry.
So it's a semantic similarity, right? It's something that is perhaps not necessarily super well defined, because there are different ways of how a model could see things similar based on categories, and the categories might be known to us, or often they're not. But right, the example, king, queen, peasant, female peasant, or something like that, where we have essentially several dimensions. I wonder whether we could sort of focus the model on one of these. If you care, let's say, our gender differences, do we have a way of maybe by regularizing or having like regularization given on a certain sample set, let's say particular deals with say gender differences or so, have we an option there to sort of nudge the embedding space into one direction? I don't know.
Yeah, I mean, with these kind of simple models, maybe I could see a world where we could create that regularization scheme. But like how with large or deep learning models, I feel like, do we have the understanding to be able to do that?
No, I mean, I don't think we have. But
Arvid, are you talking about doing that in an unsupervised manner or a supervised manner, where you have like labels of the things that you want to have good semantic?
Perhaps that's almost like a semi-supervised world, right? So say we use our standard reconstruction, but say we use on samples where we know they talk about gender-related stuff. We might use input dropout as one method, and the other one. What was the other one that they used? The one that works directly on the weight.
The second one.
Yes, but if we were sort of to to couple the type of regularization with some sort of high level label on the samples, we might be able to use it as a control mechanism. Proving that rigorously is obviously impossible, but it might practically sort of work.
Yeah, that's interesting.
I thought one of the questions I was going to put out for discussion was, oh, where is it? Maybe later down. Oh yeah, this statement I thought was interesting. We're not aware of a good metric for semantic similarity, and I guess that alluded to what you said, Arvid, right? Which is like it's actually not a well-defined problem.
Yeah, and you have some degree of freedom in there, right? So
yeah,
like a medical person talking about humans has a very different semantic meaning of say a human is talking about humans and humanity, and
totally, yeah,
and that, of course, that would again mean that you have to have a very good handle on your data set and sort of have like pre-categorization of your data, which again is costly and thus often not liked. But
it's totally like task dependent.
Yeah,
I suppose, and that's why. And that's why I thought, you know, their sort of conclusion, which is like, do not blindly use cosine similarity, is a kind of, it's like, yes, for sure. Anyone who's trying to do retrieval should not just blindly use it and not test the effectiveness of it on that particular problem, whatever problem it is you're trying to solve. Because it's just that, yeah, it's like saying, like, don't blindly use random forest on like a particular classification problem. You should test it. Yeah, but I don't know if anyone else had thoughts on this, on like how would you create an experimental setup for semantic similarity?
But thank you very much for that. Very interesting. Bye-bye.
Thanks, Arvid.
So I watched this talk by this guy who specializes in reinforcement learning called John Schulman. He's one of the founders of OpenAI, and he was talking about using about language, and he said language is fuzzy in the sense that like words can have multiple meanings, not like in different contexts, but also there's like a lot of nuance in those meanings sometimes. So it is maybe if the semantic concepts that you're dealing with are like very easy to distinguish from each other, then you have a much more clearly defined problem. But if you're doing it with most real world stuff, I mean, I don't even know. I wonder if it's even possible to prove that it's not possible to like have an interpretable way of understanding the semantics. You know, like, I don't know how to put it exactly, but just the idea that you can come up with some metric of an embedding space which tells you exactly the semantic difference between two words seems like an impossible feat.
Yeah.
But who knows? Maybe one day, because I feel like I'm constantly being proved wrong. Like one day we'll have some kind of metric which quantifies semantic difference in a meaningful way.
I wonder if like it's a bit like an entailment problem, or reminded me of an entailment problem, like where you have one statement, you have like another statement, and then you have to it's sort of a way of describing whether one can imply the other. And I wonder if you could do a similar thing with similarity. It's a bit more fuzzy.
Yeah.
Particularly, yeah, when you're talking about just like abstract concepts.
You know, I was thinking to myself, I wonder if this stuff would be better represented as a probability distribution as opposed to a vector. Which is actually what encoders use, like variational autoencoders usually do. I don't know. it's a whole can of worms. There's people who have spent their entire lives studying this topic. It's hard to know what's correct.
But if in that case, like the training would become difficult, the loss functions, they would become intractable when you're doing you have a probabilistical representation, as was the problem with variational encoders. It's never a win-win.
Cool. Well, thanks everyone for coming to the paper club.
Thanks, Gerard, for presenting.
Yeah, of course. Hopefully see you next week.
Yeah. Have a good weekend, everyone.
Peter, love to hear.
Yeah, sorry.
No, I was saying it's great to hear your voice after a whole year.
Yeah, welcome back, man.
And Albert as well. Yeah, I think he's gone. Yeah. If I get time, it'll be great to chat again next week. All right, take care, everybody.
Take care.
Sounds good. Yeah.